So our next speaker is Petros Toupas from Heronic Technologies, where he's CTO. He's going to be talking about automating the design of bespoke AI accelerator IP. He is a machine learning engineer specializing in computer vision, deep learning, and hardware acceleration. Nearing the completion of his PhD at Imperial College London, his research focuses on FPGA-based acceleration of CNNs, innovative methods to optimize performance, resource utilization, and automation tools. He has extensive experience developing AI solutions for robotics and edge devices. His experience on collaborative European projects demonstrates his ability to translate advanced research into practical applications, delivering impactful solutions and valuable technical expertise. He is based in Thessaloniki, which I think is Greece.
Yeah, that's good.
Okay. It's probably a lot warmer where you are than it is here. Okay, over to you. Thanks, Petros.
Yeah, thank you very much for your introduction. And I'm really happy to be here and have the opportunity to present the work we are doing in Heronic, where we are using AI to design bespoke AI hardware. We are at a fascinating intersection in technology where AI is evolving rapidly, and there is a need for the hardware community to keep pace. AI is evolving in an unprecedented rate, and each month brings new architectures and approaches. On top of that, the edge computing is becoming a necessity for real-world AI applications. And on the other hand, we are approaching the end of Moore's law, meaning we cannot rely on just the technology to scale up anymore. This is why there is a growing need for custom accelerator solutions in order to keep up with the rapid changes in the ML community. But there are quite some challenges that we face in the semiconductor industry when designing AI accelerators. While the FPGAs offer incredible flexibility and allow for high customization, they also introduce great complexity when it comes to designing efficient architectures. The diversity of operations in neural network models, the large number of tunable parameters in the hardware architecture are just some of the reasons that lead to a massive design space, which needs to be explored in order to find optimal solutions. There are various trade-offs that need to be explored, such as the performance versus resources, the on-chip storage versus off-chip bandwidth, and many, many more. So a question here is, how can we quickly and efficiently explore this huge design space? The management of the on-chip memory is another huge challenge when it comes to FPGA designs, and especially when it comes to streaming architectures. We'll talk about the streaming architectures a bit later. Take, for example, the Resonant 50. It requires nearly 90 megabytes of memory for its parameters. Even the much smaller MobileNet V2 needs 13 megabytes, and just to remind you, this is just for the parameters of the model. So why do we care about keeping the parameters on chip? So yeah, basically because this can lead us to quite substantial performance gains. But as we can see, even on big FPGAs, such as the Alveo U200 models, U200 card, models parameters cannot entirely fit in the available on-chip memory. So we need to find a way to effectively manage this available memory of the device. In many AI models, we are doing calculation with zeros, lots of them. And this is a challenge of sparsity, and it's both a problem and an opportunity. In neural network workloads, a good portion of both the weights and activations contain zero values. Even though these calculations could be skipped and utilize the hardware resources elsewhere, this is not always the case, and it's not an easy task to solve either. So by performing calculations with zeros, the underlying hardware is not being efficiently used, wasting both computational and memory resources. But what if we could dynamically choose to skip these calculations? So how do we solve in Heronic these challenges? What me and my colleagues have been developing during our PhDs is a tool flow that automatically designs objectively optimal AI hardware. It very simply takes the AI model, the constraints of the technology, and the performance objective, producing the best hardware for that specific application. The heart of our tool is a library of bespoke, parameterizable RTL blocks, which are compatible with all FPGA devices. The rest of our tool flow components are powered by AI. AI assists us in predicting the properties and performance of the hardware, allowing us to find optimal solution in days rather than months, speeding up dramatically the design space exploration. We also utilize AI algorithms to solve the optimization problem to find best mappings between AI models and hardware. Let's dive a bit deeper into the specifics of our architecture style. But before doing that, let's examine first the single engine architecture style with a systolic array. Its homogeneous overlay structure supports the execution of multiple different operations of a neural network model. This generalization often leads to underutilization of the device, since not all layers require the same amount of computations. Both the parameters and the feature maps are streamed from the off-chip, which introduces high bandwidth requirements. The execution of the layers of a model is guided by instructions from the host, and it's done sequentially, with the outputs being sent to the host after the execution of each layer, or even part of a layer. On the other hand, what we do is we have adopted the style of architectures, which is the streaming architecture. This is a heterogeneous solution where each layer of a neural network model has its own bespoke hardware compute unit. Due to its per layer bespoke nature and resource distribution across the layers, is optimized, leading to much higher utilization of the device overall. The feature maps between the model's layers stay on chip and flow from each layer to the next one in a deeply pipelined manner. The parameters of the model are mostly on chip, but when needed and necessary, they can be streamed off from the off-chip memory. The execution of the model is hostless and data-driven, meaning that the input is fed to the first layer and no further communication or instructions from the host is needed until the final results are produced. See, here we can see an example depicting this deeply pipelined execution that we previously described in a series of convolutional layers. We can observe that apart from the initial parts of each convolution, where the pipeline needs to be filled with data and introduces a small delay, this style of architecture allows for a high utilization of the device, with multiple layers being executed at the same time, each of them having its own bespoke hardware and allocated resources. Following, I will elaborate a bit more on how we explore the trade-offs and optimize these NN models during our design space exploration. So our approach is to design, as I said, bespoke hardware blocks tailored to the needs of each layer of a model. The convolutional layers are the primary computational blocks and contribute the most to the total computations of the entire CNN. The three core modules comprising a convolutional layer are the on-chip memory, where we need to store the layers parameters, the sliding window engine, and the matrix vector engine. These modules can be customized and tweaked based on each layer's characteristics and requirements. By altering the numbers of these modules, we explore the trade-off between resources and performance. For instance, one layer might require more memory, while another might need more computational power, and thus we allocate resources accordingly. This way, we can optimize and provide bespoke hardware for each specific layer, leading to a heterogeneous design. Here, we can see a more detailed view of the level of parallelism that we are exploring during the design space exploration on convolutional layers. We can have NI numbers of sliding window engines, which is the parallelism we exploit in the channels in the input of the model of the layer. The sliding window engines feed the matrix vector engines, in which we can explore a different level of parallelism, K, which is related to the kernel size. Finally, the accumulation of the channels for each filter is the third level of parallelism we are exploiting. All these factors are exposed to the optimizer, and during the design space exploration, alongside with our performance and resource models, we are able to quickly and efficiently explore this huge design space of the available design choices. So by changing also the word lengths and quantization per layer, we can achieve a fine-grained control of the model compression. This kind of control allows us to explore the accuracy versus the resources trade-off. For example, reducing a layer from 16-bit to 8-bit can significantly reduce resource usage while maintaining acceptable accuracy, and can potentially lead to performance improvements. Another way to free up the on-chip memory resources is by evicting parameters to off-chip. This choice allows us to explore a different kind of trade-off this time, and this one is regarding the on-chip memory storage versus the off-chip memory bandwidth. This transformation is particularly useful for models with a large number of parameters, where the on-chip of the target device, the on-chip memory of the target device is not sufficient enough. This specific example shows how the mapping of a ResNet 18 model to an FPGA can lead to VRAM usage exceeding available resources. As you can see, the memory requirements for that model, even though it's quantized, far exceed the available VRAM resources, meaning we cannot fit it on the device. So here is where our parameter streaming architecture comes into play and allows us to evict some of the weights to the off-chip, freeing up on-chip memory. By using a DMA scheduler, we can fetch weights from the off-chip as needed and balance memory bandwidth and performance. This approach allows our design space exploration to explore the trade-offs between the on-chip memory usage and off-chip memory bandwidth, which in the end can affect the final performance of the design. Let me demonstrate how we can get these performance gains exploiting this trade-off. In this graph, we see the FPS over the normalized on-chip memory for multiple design points produced during the design space exploration in the vanilla version and in the version with the parameter streaming. Let's see first the orange design points, which is the vanilla approach, by splitting the graph into 3 regions. The first one is from 0 to 1.25, where the vanilla approach cannot fit in the device, resulting in not a single design point. In the next region, which is from 125 to 175, the vanilla approach does produce a few designs, but they are too discrete due to the constraints of keeping the parameters on chip. And in the final region, we have our designs have converged and becoming compute bounded. Now let's investigate the blue design points, which are the parameter streaming approach. Now the design space exploration produces multiple designs in the first region and can actually fit into the device's memory. Additionally, we see that the design choices here are much smoother due to the fine-grained control of the memory allocation. Finally, we also observe that we can reach the peak performance with less resources compared to the vanilla approach. But at the start, we have also discussed about the challenges and opportunities of exploiting the sparsity of the neural network models in order to improve the efficiency and the performance of the accelerators. By doing that we could achieve better resource efficiency and skip redundant operations by reducing the number of MAC operations required for the sparse layers. So our sparse vector.product mechanism routes only non-zero operands to MACs, reducing the unnecessary computations. The non-zero checker blocks identify the non-zero weights and inputs and dispatches them to the DSPs for execution. When zeros are detected, the respective flags are triggered, skipping the specific computations. So in this example, we show how a dense implementation is using more DSP resources in an inefficient way, while the sparse design on the right is able to achieve the same performance with just 1/4 of the DSPs used, utilizing the mechanism we described in the previous slide. And here is a graph to further elaborate on how sparsity can lead to more efficient use of the hardware. In this case, we examine a convolutional layer with a 3x3 kernel. As we can see, the higher the sparsity is, the less the MAC hardware is needed to reach the max performance. If you notice, using 9 MACs is always going to give us the best performance, no matter the sparsity. But as the sparsity increases, we observe how less and less MACs are needed in order to achieve that based on the architecture that we propose. So using our design space exploration, we are searching for all these different design choices and options, and in order to end up with an optimal and more efficient design. In the figure on the right, we show that our sparse vector dot product approach always achieves better results than its dense counterpart, while at the same time our approach outperforms previous state-of-the-art solutions in models such as VGG16 and ResNet 18. We have also tested and validated our technology and designs in the ML Commons benchmark, and more specifically to the MLPerf Tiny, which is designed for AI running on embedded devices. We achieved the lowest latency in 3 out of 24 submissions, making us one of the fastest FPGA submissions of all time. This graph showcases the efficiency of our designs, not only in terms of performance, but in terms of energy per inference. Our MLPerf Tiny designs achieve ASIC level performance while at the same time exhibiting microcontroller level energy consumption. Here is a more detailed comparison for the classification task in MLPerf Tiny compared to another FPGA-based streaming architecture that uses FIN and HLS4ML tools. Our FPGA design outperformed FIN's one in latency, performance, and accuracy on this specific task, even though our quantization scheme was on 8-bit compared to the 1-bit quantization of the other design. Finally, I would like to showcase you how our technology is well suited for the latest generation of YOLO models as well, which are not for the performance and efficiency, but also for the complexity. So YOLO models have a large number of parameters, have very deep skip connections, and quite a heterogeneous architecture, which makes them quite challenging to accelerate. As shown here in the graph, using our DSC, we are able to find Pareto optimal points, balancing performance and resource usage. Through that, we were able to outperform other works, both in terms of performance, density, and accuracy. This is a result of our design automation, and that allows us to support a much wider range of models and achieve state-of-the-art performance. We were also able to beat NVIDIA's Jetson TX2 with this design in terms of latency for the YOLO V5 Nano model. Depending on the target device, our hardware is up to 7 times faster than TX2. With our deeply pipelined architecture, we also ensure that models' outputs arrive quickly and we are not bottlenecked by the off-chip memory bandwidth. Concluding, I would like to emphasize that our toolchain is able to produce objectively optimal and state-of-the-art accelerators. We are able to support a wide range of applications, ranging from TinyML to object detection and image classification. In all such applications, we have achieved state-of-the-art performance in research, and in certain cases, even beating industry. Thank you for your attention.
Are there any questions in the audience? Oh, sorry, it's the journalist.
Yeah, so I noticed when you had the results, you were showing your speed up. You had various models. You had ResNet 18 and you had ResNet 50. And my question is, on ResNet 18, you got 50% speed up, and ResNet 50, you got 15% speed up, and they're really the same model, just with more layers. You almost think it would be more sparsity with more layers. Why didn't you get such a big speed up with ResNet 50? Have you got an understanding of where that speed up is coming from?
You can repeat any question.
No, I think I can hear it coming through. Did you get the question, Petros?
Not completely. I think I get the main point that has to do with why, correct me if I'm wrong, why the speed up on ResNet 50 is not the same as on ResNet 18, right? Yeah. Here you can see that the device used, I mean, maybe it's not that obvious, but the device used is not the same. So that's probably due to some device constraints, the speed up is not as would be expected in the ResNet 18 case. But yeah, your point about more layers exploiting more sparsity is correct. But in this case, we had evaluated our ResNet 50 in another device just to be one by one compared with the other design that was available. So that's why the speed is less, because we are constrained by the device pretty much.
There is one question on the backyard outperformance of NVIDIA. You claim 7x. Is that on specific applications, or is it across all applications that 7x performance better than NVIDIA?
No, that 7x is for specific application. I mean, for YOLO V5N model, and specifically for object detection, and compared to this specific board of NVIDIA, which, to be honest, quite old. But yeah, it's for this design shown here.
Okay, that's just for object detection, yeah. And one more question online, last question online before we go back to the audience. As well as object detection, what other applications is this technology well suited for?
Sorry, I couldn't catch the question.
I'll repeat the question. As well as object detection,
yeah,
what other applications is this technology well suited for?
You mean our tools? What kind of applications can support?
Yeah, you mentioned object detection and the other applications that this is well suited for, please.
Yeah, I mean, we are not constrained by the application. We are able to accelerate any kind of CNN models. So that's kind of application independent. We can work on classification, on segmentation, and we have such kind of results on different kind of models on different applications.
Okay, so you mentioned classification and
yeah,
okay.
Classification, image segmentation, human action recognition. These are all models that we have deployed and tested on our technology.
Okay, I don't think there's any more questions from you. Oh, there's one at the back. Do you want to come up the front because the microphone's here? Thank you. One more question, please, Petros.
Yep.
Hey, Petros. Thanks for the presentation. My question is, in your tool chain, you have the AI model going in. Is that already a sparse model, or your tool chain makes it sparse to exploit the sparsity? Thank you.
Yeah, thanks for the question. When it comes to our tool chain, we expect the models to be already at the state where the tool needs it. So in terms of quantization, for example, we expect the model to be quantized before coming into the tool chain, and same goes for the sparsity. Given that, we have our tool flow to map it and optimize it for a specific target FPGA.
Okay, there was one follow-up question on that online, actually. Given the reliance on the sparsity, how common is this sparsity? Is it evident in all applications, all AI models, or is it just a few AI models that have this sparsity?
I cannot speak with numbers at the moment, but based on my experience and from how I perceive this sparsity thing, most of the AI models exhibit quite a lot of sparsity. So you can go for more details on the paper, because I don't remember the numbers for that, but I'm pretty sure the sparsity is apparent in quite a broad pool of models in the CNN models.
Okay. No more questions. Thank you very much. Thank you very much, Petros.
Thank you.